Hello there, Mr. Sutton here, bringing you the Algebra 2 10-1 lesson on right triangle trigonometry. In this one, we will find sides and angles in right triangles using trigonometric ratios, which you might remember as SOHCAHTOA, and we're going to solve some real-life trig problems involving angles of elevation and depression. To start this lesson off, we're just going to dive right in using the different functions that we're going to use throughout the lesson, and also kind of refreshing how to do them on a calculator. So pause the video and just try entering sine of 30 degrees into your calculator. Alright, now when you're doing this, couple things to keep in mind. First off, you need to be in degrees mode, and also, because you're in degrees mode, it turns out you don't need to enter the degree symbol in when you do this in your calculator. So let's go to Desmos. So here we are in Desmos. Now notice it says DEG right here. This is how you switch back and forth between degrees and another mode called radians, which we'll get into in another lesson. It's just another way of expressing angles that looks different numerically. So if I'm in degrees and I do sine of 30, and I don't need the degree symbol, it comes out to 0.5. Now if I switch that to radians, I get some other completely different crazy decimal. So I want degrees for everything I'm doing with triangle trigonometry. So this comes out again to 0.5. Now just real quick, it turns out that the scientific Desmos calculator defaults to degrees. Interestingly, the graphing version of Desmos defaults to radians. So normally you would see this in radians if you just come in here, but you need it to be in degrees again if you're going to come up with the same answer that we are in this lesson. So now that we've got sine of 30 out of the way, try out cosine of 40 and tan of 82. And I do recommend the scientific version of the calculator. Alright, so going back to my scientific Desmos, let me clear that out and put in cosine of 40. And that's about 0.766. Just take it out to 3 decimals. And then let's do tan of 82. So tan, T-A-N, 82. Pretty easy to enter these in, and that comes out to 7.115. Alright, so $1,000,000 question. What did we just do? We just entered some random functions in the calculator and got some random numbers, but what are those actually doing? Like with the square root function, we know kind of what the square root function is actually doing mathematically, even if we couldn't do it ourselves without the calculator. These we have no clue, so let's dig a little deeper into what these are. So sine, cosine, and tangent if we actually spell them out, or we can abbreviate them with their function abbreviations. These are what are called trigonometric or triangle-based functions. They take an input, which is an angle, and this weird little symbol here, this 0 with a line through it, you might have seen this. This is theta. This is basically just the angle version of x. It's just letting you know, hey, I'm going to plug an angle in for this variable. So the input is some angle, and the output, well, that's another $1,000,000 question, like what are these weird decimals? It turns out that the output is the ratio between two sides of a right triangle that has whatever angle you're plugging in there. So let me draw out some right triangles. Here's 2 of them, and again, right triangle means we have one 90-degree angle in there somewhere. So in order to make sense of what I'm about to show you with these different functions, we need to have a way of naming the different sides of these triangles. So we'll start with the one you probably know the best with a right triangle, and that would be the hypotenuse, HYP for short. And as you might remember, this is just the side that's across from the right angle. So in this triangle, we'll do this left one first. This is our hypotenuse right here. Now there's 2 other sides that we can talk about. We could just call these other non-hypotenuse sides the legs of the right triangle, but we can also be a little bit more specific. For example, the opposite side, OPP for short, this is the name we give to the leg that is across from the given angle. So in this triangle, let's say that they actually gave us this little blue theta angle here. We could call the side across from this angle over here the opposite side. And then we also have a way of talking about that third side. We call that the adjacent side, ADJ for short. This is the leg touching your given angle. So we have 2 legs on this angle. One of them is or actually I should say we have two legs of the right angle. One of them is this opposite side. The other is touching the given angle here, and this is going to be called the adjacent. Now, if you get a little bit confused about these different names here, one way you could think about this is sitting at a triangle-shaped dinner table. Let's say that this is you, this little theta right here, and the opposite side is sitting across from you at the table. The adjacent side is sitting next to you. Adjacent means right next to. So pause the video real quick and see if you can label the different sides of this other triangle. All right, so here's our hypotenuse. Opposite side is going to be across from the given angle, so that's now down here. Notice it changes as you change where you're sitting at the table here. And then the adjacent side is again touching the angle. It's one of the right angle legs that's actually touching the given angle here. Now, why did we go to the trouble of figuring out names of different sides of a triangle? Because these three trig functions, each of them is the ratio of two of these three different sides. We'll start with sine. The sine of theta is the ratio of the opposite side over the hypotenuse. Opposite over hypotenuse. So if I know what those numbers are and I stick them in a fraction, that's what this crazy decimal is right here. And now the cosine of theta that we did right here, that's actually the ratio of the adjacent side over the hypotenuse. And then finally, tangent of theta, that is the opposite side over the adjacent side. So these are three good formulas to remember. We're going to be using these constantly. If you have trouble kind of figuring out which is which, a good way to remember them that we've been using for probably a good century here is the acronym SOHCAHTOA. So S-O-H, that's the sine opposite over hypotenuse. Ca, C-A-H, that's cosine equals adjacent over hypotenuse. And then TOA, T-O-A, that's the tan equals opposite over adjacent. So I usually write this first thing whenever I see a right triangle where I have it one of the angles. Now that we've gone through kind of some of the nuts and bolts of right triangle trigonometry, let's actually use it on a problem. So in general, this whole SOHCAHTOA business is going to be used whenever you have a problem involving two sides and an angle. You'll remember that all your SOHCAHTOA ratios have two sides in them and an angle. So you might know two sides and be trying to find an angle, or you might know, like in this situation, one of the sides and an angle and be trying to find the other side. So it's one of those two situations. So when you have one of these problems, good idea to write down SOHCAHTOA. If it's a right triangle, you can use this kind of thing. And then we need to basically choose the function out of these three that this acronym gives us that has both the given and the requested side involved in it. So you need to figure out, this 10, this x, which sides are they? So just kind of thinking this through, x is the hypotenuse. That's the easiest one to pick out since it's across from the right angle. 10 is across from the given angle, so that makes 10 the opposite side. So we have O and H, that's so. So that means that we would use our sine of theta equals opposite over hypotenuse ratio here. So once you've figured out which trig function to use, all you need to do at that point is plug in the sides and angles and go ahead and solve for whatever was missing. So pause the video and see if you can finish this one off. Alright, so plugging things in. We've got the angle here, theta, that's this 27 degrees. The opposite, we said, was this 10, and our hypotenuse is x. So we can write sine of 27 degrees equals 10 over x. And now to solve for x, we can do this in one step if we wanted, or we can take two steps to do it. We need x out of the denominator, so I need to multiply it to the other side here. And then I can divide by sine of 27, and I have to divide by this whole sine of 27 expression. It's one big thing. It's basically one big crazy decimal. And then I can just plug this in the calculator. Now, if you didn't want to do this in two steps, you could just switch the x and the sine of 27 when you have this situation. It's kind of like a cross multiply situation. But now let's go to Desmos and plug this in. And again, when you're doing this, you're going to want to make sure you're in degrees mode. So let's do 10 divided by, and then we'll do sine 27, and that comes out to 22.0 if we round this off to the nearest tenth. For this problem, it's going to be a little bit more involved. They're telling us to solve triangle ABC, which means we want to find all the sides and angles here. And we're going to be using the diagram that they've given us and these given measurements here. They've given us angle A and side B. And in case you're wondering, angles are uppercase letters and sides are usually, they've got lowercase letters to represent those. So we also want to round our answers to the nearest hundredth, so a little more accuracy than the last problem. So a good way to start these problems is to label your sides and angles on the diagram. It makes it a lot easier to visualize things. So angle A was 28 degrees, that's right there. And side B was 15, so that's over there. And in order to figure out the rest of this now, usually the easiest thing to figure out next is going to be the angle, because we know that the non-right angles in this triangle have to add up to 90. I mean, just to kind of review, we know the angles of a triangle add up to 180. You've already used up 90 degrees here with this right angle, so you know these remaining angles have to add up to 90. So we could very quickly figure out angle B based off of that, and I'm going to let you go down that path in a minute. One thing to do after that, though, is finding these other missing sides, A and C. Now, to find the first of those sides, whichever one you choose to find first, you're going to need SOHCAHTOA. You've got an angle, you've got one side, that's a total SOHCAHTOA kind of situation. Once you've got the other side, you've got a choice. You can use SOHCAHTOA again to find the third side, or since you'll have two sides at that point, you could use the Pythagorean theorem for the third side. So however you want to do it. So pause the video and see if you can find angle B and sides A and C. Alright, I'm going to find things in that order that I just mentioned. So let's do B first. That's going to be 90 minus 28. Pretty quick to get that angle. So that's going to be 62 degrees. And now I'm going to figure out side A. Now I could put 62 degrees in here and use it, but I'm actually going to lean towards using the sides that they've given me and the angle that they've given me as long as I can, because I know that this 28 and this 15 is actually correct because they gave it to me. Anything else I find might be incorrect. So, you know, if I mess this up, but I, do the rest of it correctly using what they gave me, at least I won't get everything wrong, right? So to find side A is opposite from 28. And B, which we already have, is adjacent. So that means using my SOHCAHTOA sort of thing, I need TOA, opposite over adjacent. So I'm going to use my tangent ratio. So I can write tan of 28 equals opposite side A over adjacent side 15. And now to solve for A, I just have to multiply both sides by 15 and do 15 times tan of 28 on the calculator. So let me do 15 tan 28, and that comes out to 7.98 if I round that off. Now to get side C, again I have options here. I can use SOHCAHTOA again, and I'm going to because I wanted to show you the other trig function we haven't really used yet. But you also could use Pythagorean theorem at this point since you have two sides. One advantage of the SOHCAHTOA approach, though, is that we can again reuse this angle and this side that they already gave us, so we're guaranteed these are correct. So since C is the hypotenuse, and again I've got adjacent side B, I need CA, adjacent over hypotenuse. I need the cosine ratio here. So I can write cosine of 28 now equals adjacent side 15 over hypotenuse C. And now to solve for C, I can just basically swap the C and the cosine of 28, kind of like the last example we saw. So I have 15 over cosine of 28. And if I plug that in, 15 divided by cosine of 28, that comes out to about 16.99. Now again, we could have used Pythagorean theorem, so just to kind of show you that. Pythagorean theorem, you basically need the square root of a squared plus b squared. So square root of, let's see, A was 7.98 roughly, so 7.98, and then square that, plus B was 15, so 15 squared. And again, we get about 16.99 doing it with that approach. So either way. For this next problem, we've got a different situation. We still have two sides and an angle involved, so this is still a SOHCAHTOA kind of thing, but now we are missing the angle instead of one of the sides. So in this situation, we're going to start it off exactly the same way, which is to set up a trig ratio, one of our SOHCAHTOA ratios, that has the two given sides. So pause the video and see if you can figure out what my ratio should look like, what my equation should look like with the information they've given us here. All right, so taking a look at this, we have, based on this x here, we have the opposite side, which is 9, and the adjacent side, which is 12. Opposite adjacent, that's again going to be our tangent function, so opposite over adjacent. So now I can write tan of x equals 9 over 12. And that's my ratio equation that I have to solve. Now, how do we actually solve this? I have to undo the tan function in order to get to this angle x. Basically, I already have a ratio, the output of a trig function, and I need the input, which is the angle. So in order to undo trig functions, we need to use inverse trig functions. And here's what these look like. They're basically the original trig function with a little -1 exponent on them, kind of using our inverse notation. So we've got sine inverse is how this sine -1 is pronounced, cosine inverse, and tan inverse. So you can plug these into Desmos basically as these are written here with whatever ratio inside this parentheses you want. If you don't like this little -1 sort of notation, these actually have another name that Desmos also recognizes. These are also called arc functions. So instead of sine inverse, you could write arc sine. You can write arc cosine and arc tan. So it's still the same number of button presses either way, actually. So I guess pick your poison. So let's plug this in to Desmos. And let me clear all this stuff out. And let me actually see what I'm looking at here. So what I'm actually plugging in here is I'm doing tan inverse of 9 over 12. I'm actually doing tan inverse of tan of x, which gets rid of the tan, but I never really show that as a step, although you could. So in the calculator, if I do tan exponent -1, and then I open a parentheses and put 9 over 12 in there, I end up with about 36.9. They just wanted nearest tenth, so 36.9 degrees. And again, another way of doing this, I could have written arc tan of 9 over 12. And if we do that, we see we get the same thing. If you're doing the honors version of this course, you can move on to the next problem. If you're doing the CP version, then stick around for this problem. We're going to do one more practice problem involving finding angles in a right triangle. So here's another just practice problem like that. We've got two sides looking for an angle. Pause the video and see if you can find this one. All right, so again, we have two sides and an angle, so it's a SOHCAHTOA sort of thing. We've got, in this case, the hypotenuse. It's across from this right angle, which is up here. Typically it isn't, but we can put the right angle wherever we want. So hypotenuse, and this would be the adjacent side because it's touching the angle that we're given here. So we need ka, adjacent over hypotenuse. So we've got cosine of x equaling adjacent side 7 over hypotenuse 10. And if you get these two mixed up, one thing you can always remember is the hypotenuse is always the longest side of a triangle, so there's no way we'd be writing 10 over 7 in this case. So to get x, I just need to take the inverse cosine of both sides, so cos inverse of 7 over 10. And let me go to the calculator. So cos inverse, and then 7 over 10 gives us 45.6 roughly degrees. Now, if you are doing the non-honors version of the course, this is actually the end of part 1 for you. pause the video, do some practice problems involving sides and angles in right triangles, and then rejoin us for part 2, where we take a look at some real-life applications of these problems. So, welcome back, whether you're rejoining us from the CP or continuing on in the honors course. We're going to talk at this point about some real-life applications of SOHCAHTOA and right triangle trig, and a lot of these involve what are called angles of elevation and depression, so we're just going to define these so that we kind of know what we're talking about when we see them in these problems. So let's talk about angle of elevation first. The angle of elevation is the angle between looking forward and looking up at something. So you could say between the floor and the hypotenuse. So here's a visual of this. Let's say that you're here on the ground looking at the top of a Christmas tree here. So the angle of elevation is this x right here between kind of the floor of your line of sight and the top of the tree. And, you know, is this actually on the floor or is it eye level with you? We kind of dodged that question, but I guess if you had a tree that was tall enough, it wouldn't really make a huge difference that couple of feet. So now we also have something called an angle of depression, which is kind of the reverse of this. This is the angle between looking forward and looking down, between the ceiling and the hypotenuse. So kind of an example of this, let's say that you're standing at the top of a lighthouse looking down at a ship. So the angle of depression is the angle between kind of looking straight forward to the spot that's above the ship horizontally from where you are, and the angle of looking and the side where you're looking directly at the ship. So it's angle of elevation, people tend to be okay with this. For whatever reason, angle of depression, people get mixed up a little bit, and a lot of people think that it's actually this angle right here between like looking down and looking at the object, and this is never an angle that we use in these situations. So these angles, whether it's elevation or depression, are always going to be the angles between the horizontal line of the triangle and whatever your hypotenuse is. And in fact, anytime you have an angle of depression, you could actually just think of it as an angle of elevation. This angle of depression is actually, because of these parallel lines, the same as this angle of elevation would be down here. So if that makes it a little easier to figure out which angle you're dealing with, maybe just always frame it as an angle of elevation. Now that we've talked about angles of elevation and depression, let's see how this plays out in a real-life problem. So Mount Everest, tallest mountain in the world, you might have heard of it, and you know, you might be curious, how tall is the tallest mountain in the world? It seems like a pretty fair question. I guess one way to measure it would be to go to the top, drill a hole down the center, and drop a giant tape measure. That's not a very good way to measure it, though. It'd be nice if there was another way. So let's say that we have an observer, maybe it's you, 10 miles away, standing in some village out there, and so here's 10 miles from kind of the center of the mountain. Using a homemade sextant, which is one of these little devices where you tape a straw to what is this, a compass? No, it's a protractor. Tape a straw to a protractor, hang a little pendulum from it, and when you aim through the straw, looking through the straw at the top of whatever you want, this little pendulum swings to give you your angle of elevation. It's kind of a neat setup that very low tech. You don't really need a lot of money to put one of these together. Anyway, you measure an angle of elevation to the peak of Everest to be about 29 degrees. So we want to know, again, how tall is Mount Everest? So that means we're looking for this vertical side right here. So here's the setup. This is just another SOHCAHTOA sort of situation, and we kind of came up with a picture together. Pause the video and see if you can use this now to figure out the height of Mount Everest. All right, so what do I have in terms of sides? I'm looking for the opposite side. I have the adjacent side. So that's a TOA, tangent. So I can write tan of 29 degrees equals opposite side x over adjacent side 10. And then to get x, I just need to do 10 times tan of 29. And let's see what that looks like on the calculator. So 10 tan 29 comes out to about 5.5. So roughly 5.5 miles is the height of Mount Everest. Here's another problem involving angles of elevation and depression. So from the top of a 90-foot tower, which the Eiffel Tower is probably taller, but I had to come up with some kind of tower picture, it's about 93.6 feet to a flower on the ground. So looking straight from the tower down at an angle to the flower. We want to find the angle of depression from the top of the tower to the flower. So you're on your own for this one. Pause the video, draw a picture, put stuff in the picture, and see if you can figure out this missing measurement. All right, since I'm dealing with angle of depression, I'm going to go with an upside down triangle like I had in my intro picture on these. And my tower is 90 feet tall. The tower is actually over here, but that corresponds to this side over here of the triangle. So I'll put a 90 feet there. And 93.6 feet from the top to a flower on the ground down here. So I'll put the hypotenuse as 93.6 feet. And we want angle of depression from the top of the tower to the flower. Again, it's always the angle between the horizontal and the hypotenuse, h and h. So that's going to be the x there. And now, in order to get x, what sides do I have? I've got the opposite side 90 and the hypotenuse 93.6. So opposite hypotenuse, that's so out of SOHCAHTOA. So I'm using my sine function. So I've got the sine of x equaling opposite side 90 over hypotenuse 93.6. I'm looking for an angle, so I need to take the sine inverse of both sides here to get x alone. So sine inverse of 90 over 93.6. And let's plug that in. So sine -1, and then 90 divided by 93.6 comes out to about 74.1 degrees. So if you are taking the honors version of this course, this is the end of the lesson for you. Sorry to leave you on a depressing note, but hopefully you'll be cheered up by the wonderful problems that you have on your problem set. If you're doing the CP version of the course, we've got one more awesome real-life problem for you, so stay tuned. Well, after that depressing problem, there's nothing like flying a kite to lift your spirits, right? Let's say you let out 50 feet of string on a kite, and it reaches an angle of elevation of 66.4 degrees with the ground. We want to know how far away is your friend who is standing directly underneath the kite. All right, so pause the video, try this one out. Since we have angle of elevation, we can do a right side up triangle, and then we've got 50 feet of string. So the kite is up here, you're down here, your friend is over at this right angle corner here. So from you to the kite, that's where the string is. That's 50 feet, pulled pretty taut there. And they said we have an angle of elevation of 66.4 with the ground, so that's going to be right in there. And then how far away is your friend standing directly under the kite? So you're here, your friend's here, so we're looking for this base of the triangle. So the sides that we have the hypotenuse, we also have the adjacent side, the side that's touching the given angle. So that would be cosine, ka, adjacent over hypotenuse. So we've got cosine of 66.4 equals x over hypotenuse 50. So to get x, we just have to do 50 times the cosine of 66.4. So plugging that in, cosine, 50 cosine 66.4, that is about 20.0 if we round it off to the nearest tenth. So 20.0 feet. So, KAHTOA, that's the end of this one. Till next time, Mr. Sutton, signing off.